There's one last brand new proof technique that we are going to learn in this class. And arguably, this is one of the most important, one of the most useful techniques that you will need moving on in your mathematical career. And so this is all on what's called mathematical induction. All right, so this is the last technique, right? So at this point, there's no more proof structures, no more proof techniques that we need to understand. Once you understand, you have your direct proofs, you have your proof by cases, proof by contrapositive, proof by contradiction, all of those things with mathematical induction, you are ready to tackle any type of proof that you'll need in your mathematical careers. Now, the thing that's going to be special about this is that it is going to be used when proving statements about infinitely many natural numbers and or zero. Maybe we'll include, say, you could include like maybe -1 and 0 in these, but basically you're looking at a whole bunch of natural numbers, an infinite number of these, and we'd like to prove that they are true. So an example would be something like this. We'd like to prove that 5 divides 8 to the n minus 3 to the n for all n of the natural numbers. So in this case, you could start to convince yourself, be like, well, yeah, when n equals 1, 8 minus 3, that's 5, that makes sense. N is 2, that's going to be 64 minus 9, that would be 55. Okay, maybe that's true. Why is it true for all of these? Well, proving that is very difficult. We don't have any techniques really for our disposal right now, and mathematical induction is going to be the easiest way to prove this. So the proof structure of mathematical induction. We want to understand how should I structure a proof that requires to use induction. So step one, it's going to be a three-step process. Step one, show that the statement is true for the smallest value of n you're considering. So this is called the base case. So when we have a proof, first step we're going to have is we're going to write down base case. Let n equal blah. And then we're going to show that it's true. So basically just one specific example. That example is going to be the smallest one. So here, because 1 is the smallest natural number, we would show that this is true for n equals 1, base case. Step 2, assume the statement is true for n. So we'll actually state, assume this thing is true for n. That's called our induction hypothesis. We're basically hypothesizing, say, what if this is true, right? We're going to assume that this is true. Then the provey part of all of this comes in to show that the statement is true for n plus 1. So we assume it's true for n, and we'd like to prove why is it true for n plus 1. So we'll see some examples in the next video about how do you actually prove something with induction, how does this work, but let's understand the logic of this. Why is it that if I am able to prove just the smallest numbers true, and then if this is true for n, then it must be true for n plus 1. Why does that prove that it be true for, say, all natural numbers? So if we consider p of n, let's say this is the statement that we're trying to prove. So we're trying to prove the statement p of n. So n, we know, can vary for any type of natural number. If we know p of 1, if we know that this is true, and we know that p of n implies p of n plus 1, this is also true, right? So this is what we're proving. We're proving the base case. We assume this is true, and we're showing that this is true. So we're showing that this conditional statement is true. That's what the induction hypothesis to this last step is doing. So what this says then is that for any n, this is going to hold, and I know p of 1 also is true. So if we look at what's going on with, say, p of 2, we'd like to know, why is this true for p of 2? Well, if we know that p of 1 is true, and we know that p of 1, if p of 1, then p of 2, this is also a true statement, well then we have this piece is true, the whole conditional statement is true. So remember, if the conditional statement is true and the first part's true, if the second part is false, well that makes the whole thing false. So that must mean this must be true. So this is forced to be true. Now that I know p of 2 is true, well then what about p of 3? Well, if I know that p of 2, this is something that is true, and I know that p of 2 implies p of 3, and this is also a true statement, well then again, I have this first part's true, the whole conditional statement's true, that forces the second part to be true. So this nice structure of our mathematical induction allows logic to just push everything through and just say, okay, as long as the first one's true, and for any n you have this, every single value of n in the natural numbers will hold, and we will have ourselves the statement that we're trying to prove. And so that would be, say, the structure behind this is that you would assume, or you would prove that this is true for n equals 1, show that if 5 divides 8 to the n minus 3 to the n, then 5 divides 8 to the n plus 1 minus 3 to the n plus 1, and that would be sufficient.